3 to infinity, right? Then you get
Yes. Yeah. Yeah.
Why do you think that was the question? It's like, I saw that, okay, so you're saying when you change the three-body binding energy, you kind of change three-body parameter, and this I couldn't understand why.
No, here we see that exactly the effect of the four-body parameter in the, this energy spectrum.
So you're
Yeah.
looking at the unit height?
So here we are, changing the B3 over B4.
So is this for unit height limit? For
This,
the cardinals?
yes, this is for unitar limit.
And then you have an infinite number of primal states and
Again, this is, okay, in this point, that this was just for this prediction for this point. Numerically, we see that for the ground trimer, because we are talking about the below the ground trimer, exactly in this condition, when B3 over B4n equal to 0 and at the unitar limit, we can have infinite number of tetramers.
what does this mean? It doesn't mean P4 goes to infinity?
No, B3, we can have a shallow, very shallow trimer state in comparison to the ground tetramer.
Okay.
So let me continue and then probably can discuss.
But you should clarify what this limit corresponds to. Is it correct when I say that this limit corresponds to taking the ratio of mu4 to mu3 to infinity? Or is that not correct? I want to know what that limit corresponds to in the parameters of your model.
Yeah. Yeah. So when we move this in this direction, we are increasing the scale ratio. So it means that it starts from 1.6 in this region, as I said here 21, some point here 80, and it's go to very large about.
Where are you when you hit the y-axis?
Here.
Yeah.
This is just, that we don't have the numerical result here. We have just close to this for scale ratio about 300 and 400. So this is just an extrapolation for this by using this point. Here?
Yeah, not this extrapolated, right? But
Yeah.
you have a
Here? Yeah. Yeah. For example, we can have a look to this scale ratio, 300 and 400. Ground, first excited, second excited, and one more that numerically is not easy to calculate. Yeah?
So because your three-body binding energy is 0, does that mean that you're not in the FMOP scenario anymore?
It can be.
Three-body sector?
Yeah, for this specific point. Yeah.
But why? It's like one would say that okay, you need to take always this 1.6 ratio because it was found, but why do you have to change it? Actually, yeah, let's ask this question now.
Okay, so
Just understand.
yeah.
How can you move the three-body binding energy? I think the lowest one, low energy of ground state, three-body ground state to 0.
What I claim is, yeah.
By changing the three-body regularization parameter.
By changing the, for.
Continue some of these discussions. How many more slides do you have?
I think that, I have more.
Looking at the limits, so the three-body bound state, the ground state goes as some ultraviolet momentum squared, right?
Anyway, for infinite regularization, you have to have infinite number of three-body bound states. Anyways.
Yes, but the point is that here we have an infinite ratio between the deepest tetramer state and the deepest trimer state. It's not that the trimer energy goes to 0, it's just this ratio.
The three-body bound state goes to 0. So you haven't at all three-body bound state.
Okay, let me continue. Here we have a shadow region that show that, that if we want to extend this picture for, that next trimer, because we have the binding energy ratio between two successive trimer equal to 550, So it means that we can physically we cannot have this state between two trimers. So it means that by changing this, I mean that this regularization parameter, we can have in this region 1, or here it can have 2, or at most 3 tetramers between 2 successive trimers. So here, I mean that in order to, I mean that compare results with the experimental data, we have also calculated, we have studied this loose, 4-atom loose features. It means that we are exactly at the negative scattering length, where, I mean that this is for the trimer state appears, and these are for the fast excited and this ground trimer appears. So we have compared this ratio of the scattering length for ground tetramer, excited tetramer connected to this ground trimer in this plot. Here we see that A4B2 over A3B minus. A3B minus is corresponding to negative scattering length when the trimer appears. This is when the fast excited state appears, and this is the ground state appears. So this is here that we have, I mean that a result for exactly 0 range at the unitarity limit. Here we have the other group result. I mean that this is for the stature. We have also this plus sign from the Deltuva calculation. We have the experimental data. And as you see, all of this data and numerical result are below this, I mean that curve, except these 2 experimental data that are done by the lithium ultra-cold gas that we cannot interpret. I mean that we predict that the shift or deviation from this 0 range can come from the range correction in the model. So I can show that how it can work, but we don't have any, I mean that idea for this 2 point above this curve. So now we are going to consider the range correction in the, I mean that this 0 range model. So we compare in the first step with other theoretical studies that is done for these 4-atom resonances, and then we try to see how this result can be used for the extraction or interpretation of the experimental data. So by using the effective expansion at low energy, and by considering just to this order, we can see that the transition amplitude can be, I mean that the range correction can be considered in this form. So this is the correction that we are going to consider in our 0 range model. And by this is just an example to see that how the scaling plot, 3 and 4 body scaling plot, can be changed by considering this 0 range correction. Here we have the result for, I mean that from Cornelius and Gluckler for a realistic helium-helium interaction. This is, I mean that for the 0 range interaction, this is the, I mean that the scaling plot that we have. The dot point, I mean that this orange dot point are the result that obtained for the S-wave HFDHE2 interaction. And I see that just by changing, I mean that the R0 with respect to the 3-body parameter with this value, we can have the same, I mean that result. So we have not interpreted the result, but this is just to see that how the range can affect the scaling plot. So it means that we have a shift, or I mean that in the right or the plot, a scaling plot is widened by considering this range effect. We can see the same effect in the, I mean that the 4-body scaling plot. Here we see that when R0 is 0.01 over mu4, of course mu4, I mean that is not a physical quantity that we can work. This is just, I mean that to see how numerically can this plot change. So we have this diamond green point that we see that if we go to the right direction, where we have the other group result, this can, I mean that wide the plot or can have a shift to the right. So we have also for a larger value, I mean that this blue diamond, here we have more shift in the right. So it means that if even we are doing the calculation at the unitarity limit, considering the range can, I mean that have a shift to the scaling plot. So here we have some, some section of the plot in comparison to hammer and platter result. This is just, that sample calculation that we have done to see that we can have the same result by, for, the positive scattering lengths by, that hammer and platter. Here, the comparison with the stature, we see that again, that in this section, we can have a shift to the right, and also in comparison with the delta results. So,
let me just
yeah.
remark that these points in the upper plot, they are not fully converged. And
Yeah.
when I send you the points, I
Yeah.
wrote you this.
Yeah.
So they come out of a plot where this difference doesn't matter much. So
Yeah, but the
I
point
think
is
we
that, yeah.
shouldn't interpret too much into those points.
No, no,
because the
I'm
points
not,
that we used
yeah.
to get our numbers
Yeah.
were not those.
Yeah, sure. But the point is that this is the result for positive scattering lengths. This is the result for negative scattering length. This is my interpolation at the unitar limit. And of course, we have also your, the conclusion for here, this point. This is the point that you, that for the ratio that 5 and 1.05, or 1. Yeah, this is, there are two different results. And what about the, the range correction in the position of the 4-atom resonance? Here we have obtained, that by considering this range correction, this scaling function that connects the scattering length ratio of the first excited tetramer, that with respect to the ground trimer, as a function of the scattering length ratio of the ground tetramer, of course with respect to the corresponding trimer, and R0 over A. So we have parameterized this function. It means that if we have R0 over A for a calculation or for an experiment, and we have the position of one of the the tetramer resonances, so it means that we can have a prediction according to this simple polynomial that we have here for the next tetramer state. So here we have the result. So it was the the curve that I showed in the previous slide for the zero range interaction. Here we have R0 over A 0.1, R0 over A 0.2, 0.3, 0.4, and 0.5. And we have also again the other theoretical result by stature, Deltuva, and Gatto-Bijou, and we have also this experimental result. If I compare, that our analysis with stature result, that is, that we try to find what is the R0 over A when we have two, that the scattering lengths of the two loose tetramers. So this is that they have in their calculation, R0 over A 0.38, and this is what we have, that we can obtain from this analysis. And for the Deltuva calculation, that he has 0.33 for this, the Gaussian potential, and this is our prediction for 0.29. So if we analyze that we have the these four experimental data by, that having these two loose tetramers connected to a loose trimer, we can see that the R0 that we have predicted is listed in this table. Of course, for different value of this, that this ratio, we can have different value, as we can see here in this plot. That here is connected to R0 over A, another R0 over A, another R0 over A, and this is also another R0 over A. So that's why we have predicted different values according to the this experimental data and errors that can be compared with the, R0 that is corresponding to these cesium atoms. So I need also to talk about shortly about the mapping that we have for this calculation, because to see that how is the accuracy of the calculation and how the result are stable. So this is just, I mean, that sample calculation. This is the convergence of the first excited tetramer binding energy as a function of the number of mesh point and the second excited. But the point is that here we are using a hyperbolic mapping for sure. By using that linear mapping, we cannot see these states because you see that we have a very small cutoff close to 0 that we can see in, that probably next slide. Here I have the example of the total wave function for u1 equal to 0 as a function of u2 and u3 for scale ratio 50. When we have rescaled the x and y axes for u2 and u3 for this, by multiplication of the that momentum and also energy with this factor square root of the corresponding energy. This is for the ground tetramer, first excited and the second excited tetramer. And by having this wave function, we can extract this momentum distribution functions. We can see that here, this is for ground tetramer, first excited and second excited for NU1. So we can see that I think that the number are not visible, 10 minus 4, 10 minus 3, 10 minus 2, and 10 minus 1. So it means that the main contribution of the wave function for this second excited is between 10 minus 4 and 10 minus 2. So it means that if we have a mapping in the momentum variable, that between the first point and the second point, the step is 10 minus 2, so we cannot see for sure this, numerically we cannot see this state, or we cannot obtain this state. So we have the same plot for NU2 and NU3, and when we rescale the axis with this, the square root of the energy, corresponding to each state, ground, first, and second, we can see that these two shallowest tetramer states can have a universal shape, and of course, comparison with different scale ratio, we see that this universality in momentum distribution function. So, as a conclusion, in our study for this weekly Four-Boson bounded state by using a normalized zero-range model, we see that it is not enough just to consider a three-body parameter as we need to, describe for the three-body system. So we need to also consider one more parameter that can move the energy level of the successive tetramers. And we can see that in comparison to other calculation, experimental and theoretical, we can say that this is a model independence limit cycle. So, and also we can conclude that between two trimers, we cannot have more than 3 tetramers, or we can have at most 3 tetramers between 2 successive trimers. Range correction leads to a shift in the scaling plot, or wide scaling plot for the 3 and 4 body case. And we can see also this shift in the range, this range correction shift in the position of the 4 atom resonancy. So that can be used for the interpretation of the experimental data. So it would be interesting to answer to this question. What about the next trimer state? That can we see the same tetramer spectrum for the next trimer? That we have done some calculation, but unfortunately I have stopped because that this is the work that I've done in Brazil, and now I'm working nuclear physics. So, but now we are also doing, following the calculation. And probably Tobias can, talk about this in this program a few weeks later. And what about the scattering atom trimer and dimer calculation? And another question is that, can we extend this picture, the Fedov-Yakubovsky formalism for more bosons or not? I can say just shortly that we have the formalism for the Yakubovsky equation for 6-body bound state problem. That means that here, for 6 identical mass particles, we need to solve 5 coupled Yakubovsky equation, which depends to 5 Jacobi momentum. Of course, it is much more complicated in comparison to the 4-body case, but for a simple calculation, we are trying to do this, to solve this 6-body Jakubowski equation for 2-neutron nucleus helium-6, which leads to, as we see here in this picture, it can be considered as a core, which is alpha particle and 2 shallow bound neutrons. But the point is that we are not considering the FEDEF picture. That it leads to 2 coupled equations, but not for neutron core and neutron-neutron. The coupled equation because of the structure that we have in the core for 3 + 1 and 2 + 2. So that's why we are going to, that the work which is in progress in my PhD supervisor in Tehran for this, to have a simple solution for this case, and in the next step we can do for the, to solve this 5 coupled equation to see that how the FMO picture can be extended to 6-boson or 5-boson system. And here we have my collaborators, Marcelo, Tobias, Antonio, and Lauro. Thank you so very much for your attention.